right, happy Thursday, and thank you all for coming. So I have the pleasure of presenting Tom, who will be presenting the session behind the app. And then after the presentation, we'll be taking questions, so enjoy. The stage is yours.
Thank you, Phil. So hello, everyone. Thank you for coming. Today, we're going to talk about using background services in macOS client applications. First, let me introduce myself. I'm Tom. I work at Jamf at the Jamf Executive Protect division. We do nation-state cybersecurity defense. So if this is something that interests you, you're more than welcome to talk to me afterwards. But today, we're talking about client applications. I mostly do back-end engineering, but when I had to delve into client applications, I found many interesting things that we need to be aware of when we do client applications and background services and how to keep it secure in general. So let's start with client applications. And we can start by asking why we even need client applications in a world that moves towards web applications. And honestly, if you can do a web application, maybe that's easier, maybe that's better. But some stuff you cannot do in a web app, and you've got to have a client application, stuff that integrates with the operating system, etc. And writing a good client application is more difficult, and making it secure is even more difficult. So we'll talk a little bit about that. And now that we have a client application, we might ask, why do we even need a background service? Like, we can have a client application without any background services, and it could work just fine. And if you can get by that, that's fine. That's amazing. But sometimes you can't. And there can be a few reasons why. One is choosing the best tool for the job. For example, maybe you do machine learning and AI, and you want to use Python because this is what all the cool kids are using. And it has the best SDK. But you want your UI to be native UI, right? You want to use Swift for your UI. You want to make your users happy. And so you have two processes for the same applications. And you would need to have some kind of communication between them. So you would have a front-facing process that would be the Swift app. And you would have a back-end service, a background service, which would be, for example, the Python app that does the AI. And you would need to handle the communication between them. And you would need to make it secure as well. So this is just one example, but there are others. And another reason is stability. Sometimes you want to run stuff in the background, and if there is a problem, if it crashes, it shouldn't crash the whole app. It makes the experience more responsive for the user. You need to worry less about stuff going wrong in case it does go wrong. And we'll talk about it later when we see that for background services, we can restart them automatically if they fail. And the operating system handles it, so it kind of lifts the effort off of you. And the last point that on why we need background services is permission separation. Sometimes you need to perform some operations with elevated privileges, with administrative privileges, and you don't want to run your app as an administrator because this is a security risk. One thing you can do is prompt the user for some admin privileges, but this can tire the user if you need to do it every single time you need some kind of permission to do something. It's way easier to just ask the user for permission once, and then when it grants it, then you can do the same operation and again because the user already trusted you. So this is also something you can do with a background service. And we'll see how we can do that. So suppose we have the background services. We need to make it work together with our app. And there are a lot of ways we can have some communication between services in our app. And we'll go over some of the main ones, and we'll discuss their advantages and disadvantages. So the first one is the simplest one. It's not the recommended one, but it's something you can do is create a shared file. One application writes to a file, the other one reads from it. Very simple. Another thing is a WebSocket. You provide an address and a port, and you can communicate via TCP/IP, as you know when you communicate with the web. You can also do it locally. You can have a Unix domain socket or a named pipe on Windows. Just curious, in a show of hands, how many of you are familiar with the Unix domain socket? Okay, not a lot. We'll discuss a little bit about it later as well. And we have shared memory, which is more complex but allows you to transfer larger amounts of data. And the last one, which is also the recommended one to use on macOS devices, not just macOS, also iOS uses it, is called XPC, cross-process communication. This is an Apple solution, and as we'll see later, it provides the best security and the best way to communicate between services on macOS. But let's go over everything one by one. Start with a shared file. Please don't use it. It's not recommended. You will have synchronization problems. It's only one way. You can create a log file if you want to synchronize it in a better way, but it's not really what it's meant to. You also abuse the disk writes for no particular reason because it's a local machine. You can just write to RAM if you, it's preferable to write to RAM instead. So I would not recommend unless you want the JSON police to arrest you. WebSockets are the next way, and I think this is the most popular way that I've seen in the wild. The same way you communicate to a web server with a socket, you can also communicate between services. You would have one service listening on some port, and the address would be a local host, obviously, and the other service connects to that port, and you can communicate maybe via HTTP because this is the standard, and it makes life very easy. But it has some disadvantages, and one of the big disadvantages is it's very inefficient locally. It uses the TCP/IP stack that is necessary for network communication, but when you communicate locally, you don't really need it. It's there to prevent corrupted data over the wire, but when you operate locally on the RAM, this is just an overhead that is not necessary. And you have the problem of deciding on a random port that another app might need to use, and you have to pray another app doesn't use it, or you would define a port range, and then you would have to iterate and find a port that is available, and then you would need to tell the other service what port I'm using, and it's getting more complicated and more cumbersome just to do some basic communication between services. And let's talk a little bit about the security part of it. There is no built-in authentication. When I listen on a port, anyone can connect to it. I don't know who connected. I would have to verify it myself in some way, but this is another step I would need to do if I'm just listening on a port. Also note, it is preferable to listen on the 127.0.0.1 IP address instead of localhost because resolution of localhost can be manipulated to go even to an external web server. So you want to do communication on a local device, and suddenly a malicious actor can connect from remotely because you didn't listen on this local host, on this local port IP address. So make sure if you do use it, then use an IP address and not a localhost service name. And the communication itself is not encrypted by default. So if you want to have the communication encrypted, maybe sometimes you don't want it because it's a local communication. Maybe it's okay if someone can sniff the communication. Maybe it's not that important of a data. But if you do, if it is sensitive data, you would need to use TLS. And so the better alternative to a WebSocket is a Unix domain socket. I know it's not very popular, but it is preferable when developing on the local machine. And a Unix domain socket is it's available for macOS and Linux because they're both Unix. And for Windows, there is an alternative called named pipe, which is similar but a little bit different. So instead of defining an address and a port, we define file system path. It's just a file on the file system. If you define a unique file system path, you can make sure no one else is using it. For example, if you use a reverse domain notation, unless a malicious actor, of course, does that. But on a normal basis, there shouldn't be a collision. And the file itself is not a normal file. It's not a file on the file system, as in you can write to it and there will be data on it. Everything you write to it, whoever listens to this socket gets the data. So it's very easy to use. You can use it just like a file. You can read and write to it, similar to like a WebSocket. But you don't have the TCP/IP stack. So it's way faster. And I think it's about twice as fast because you don't need to pack it into TCP/IP packets and then unpack it. So it's just way faster. And if you want, you can even do HTTP over it. No problem with that. You can still use your loved protocols, just not over TCP/IP. Just use it over a Unix domain socket. And with the security side of things is where it gets a little bit complicated. The security is the same as security as file system pass. So you have a certain user that owns the socket, and it has a group, and each one of them can have a read, write, or execute permissions, which is good, but it's not very good because it's a permission that's based on like a single user or in a single group, and if you want to have multiple of these, then maybe you would need to set up a few users and have the permission set up, and it's a bit cumbersome. So let's see an example on how we can use the Unix domain socket to do some kind of secure communication. You can listen on a Unix socket, and then there are some functions you can use to get the PID that connects to this socket. And from the PID, you can get the executable path. And from the executable path, you can verify, OK, this is the executable I'm expecting to read from. And you can even verify the code signature of that executable. And this is not something you could do with a WebSocket. So this gives you a little bit more confidence that whoever connects to you is verified. Because if you verify the signature of the executable connecting to you, you can verify it's someone that you trust. So this is another advantage of using Unix domain socket as opposed to WebSocket, as opposed to the other stuff that we said. It's also strictly local. So there is no way someone from like outside can connect to it. Windows uses something called named pipe. So here we have a pipe called John. And it's very similar to Unix domain socket, but you have a bit more granular control over users and groups. So it's actually implemented a little bit better. But you need to be careful because by default, you have remote access. So this is not strictly local for Windows. Someone remote can connect to it. So you will have to define it to be only locally accessed if you use named pipe on Windows. So you need to be careful about that because by default, it's not like that. We also have shared memory. I'm not going to go too much about shared memory. This is mostly useful for large data that you want to transfer when you want to do it efficiently. It's rather complex. You need to handle the synchronization manually in the code. And there is no built-in authentication. But if this is something you need to do because you have a lot of data, this is the best you can do. And now the cherry on top, XPC. XPC is Apple's unique proprietary communication between processes. It's on macOS, it's on iOS, I believe it's also on watchOS, it's everywhere. It's used by the operating system processes, and you can also use it yourself in your own application, and this is what we're going to see today. The usage is a bit more complex than Unix domain socket, but it allows you security from the get-go by default. Everything that goes through XPC is validated by the signature of the executables that connects to it. So you don't even need to do it manually. You could check which signature it is, but you do know it is signed and verified. So this is really nice. And if it's not signed and verified, then the communication would just be blocked by the operating system. So actually, XPC is based on something called Mac ports. This is a low-level concept. I'm not going to go too much over it, but in high level, Mac port is something similar to Unix domain socket. It is packet-based as opposed to Unix socket where you can send a stream of data. On Mac port, you need to send data in packets. And the permission, the security part of it is having port rights. So you have send one, and receive. So if you create a Mac port, you can give some access to another service to connect to this port, but you can limit it to only sending something, sending like a single packet if you want, or if you want to send the other process something, you can give it the permission of receiving. And now there is the question that comes up, like why do we have Mac ports and Unix domain socket in the same operating system? And it's a bit weird, like why do we have two ways to do the same thing, right? Like we have WebSockets, but this is for web communication. Why do we have Unix domain socket and Mac ports? And this is where we head into a small story time. Back to the 90s, you might be familiar with Steve Jobs. At some point, he was laid off from Apple, and he founded a new company called Next. And this company developed an operating system called NextStep. And NextStep had a really good software, and it was kind of a mix of a fusion between kernels, between BDS and BSD, I'm sorry, and some kind of Mac kernel. So it has a POSIX compliance, which means a Unix domain socket, but it also had its own, let's say, mechanism using Mac ports. And actually on macOS, Unix domain socket is implemented on top of Mac ports to support POSIX compliance. So we get the best of two worlds. And then because it was so good, Apple acquired Next and acquired Steve Jobs back in, and the rest is history. But yeah, it's based on a microkernel architecture, so you can have, the kernel is very small, but you have processes that communicate with each other with XPC messages, and they needed to make it secure, and this is how they implemented it using Mac ports. But we are going to focus on XPC because this is the higher level construct of communication. So I have a small code example. This is in Swift. This is pseudocode, right? I kind of trimmed it down to make it more visible on screen. But basically, if you want to have an XPC service, you can create an XPC listener, and you would get some kind of service name, or you can put yourself a service name if you want. And then you would need to export it, and then when some connection comes in, you can verify it's from certain bundle ID or certain team ID. And again, the operating system verifies that everything here is signed, so you just need to check that it's signed by the correct signature that you want. Now that we talked about XPC, let's talk about the constructs that we can define using XPC, and those are LaunchAgents, LaunchDaemons, and login items. This is how de facto you define background services for your application. So this is how it looks like. Basically, a launch agent or a daemon is just a plist that you define, and you give it some kind of bundle ID. You give it some path to your executable, to your app, and you tell it when you should run. So for example, here run at load means run at like when the user logs in. And actually you can, it's very, very flexible. You can have a lot of different conditions on when you can run your launch agent or daemon. Excuse me, I forgot to say, launch agent is for background processes that run with user permissions. And LaunchDaemons are background processes that run with elevated permissions. And login items are just special case of launch agents that makes your application run at startup. So other things we can do to make other events that we can subscribe to launch our launch agent or daemons are file system event changes. For example, when you create a file, delete a file, when you mount external drive or unmount, when you connect to Wi-Fi or when Wi-Fi disconnects, when you log in, when you log out, when your computer goes to sleep or hibernate. You also have when the screen locks and unlocks, when you connect a USB, and even you can even filter by what type of USB connected. So for example, if you only want to run something when you connect an iPhone, you can do that. And also a cron job, you can just run services on a time basis, date basis, and everything can be configured using this configuration. So in the past, before macOS Ventura, all the launch agents or daemons had to be stored in the library folder of the user. And this is something that was a bit cumbersome because you would need to, when you bundle your app and you distribute it, you would have to put it in the user folder. So if you distribute a DMG, when you start your app, you would have to put it there in some kind of code. Or if you use a PKG, you would need to use some kind of post-install script. So not very convenient. And another problem is that it doesn't have to be signed. You'd have this configuration. Maybe it would have the proper file permissions, but it was not signed. So it could be tampered with if your computer was compromised. But this was the old way. And the way you would launch or make it available, the launch agent, is you would use the launchctl command, and you would give it like a start, stop, and this is how you could start your launch agent from your application. After macOS Ventura, you don't have to put your launch agents or daemons configuration in the library folder. You just bundle it inside the app, like in this location inside of your app. And this is way better because first, it's signed. Second, it's part of your app. You don't need some special code to install it. And also, when you uninstall the app, when you delete the app, you don't have any junk left behind. So this is the recommended way going forward. If you look at your MacBooks, you will probably still find a lot of the old ways, probably to support older version of macOS. But going forward, this is the recommended way. When Apple did this change, they also added another restriction that you cannot auto-enable your launch agents automatically. The user has to give its permission. Even if you're an administrator, you cannot do that. You would have to point your user to go to the settings and enable it in the settings menu. I will show you very soon where it's at. But this is something you need to be aware of. However, you can bypass it with MDM. So if you're using MDM, you can auto-enable launch agents or daemons for your client applications with the MDM, and the user doesn't need to do anything. And last is login items. As I said before, login items are just basically launch agents, very simplified ones that make your app run at startup. It can be enabled and disabled in the settings. We'll see in the next slide. And something to be aware of is that if you are using Bash script for login items, don't use an OSA script to add your login items. I'm not sure how many of you try to add the login items with OSA script, but it prompts the user with OSA script trying to add the login items. And this is not very professional, and the user doesn't know what is an OSA script. But if you do it using, for example, Swift or some kind of bindings, if you use some other app, you will get your app icon and app name trying to add this login item, and the user can accept it. And it knows what it is and not just an OSA script. So just a PSA here. And this is how it looks like in the settings. If you go to General and open at Login, this is where you can see all of your launch agents and daemons. So the first section is the Open at Login. This is the login items. The user can add or remove them. And if you use an MDM, you can see some of them are grayed out. You can prevent the user from removing login items. And down below, app background activity, this is where all the launch agents and daemons are defined. And again, by MDM, you can prevent the user to disable or enable those launch agents or daemons. But if it's not by MDM, you can tick it on or off. You might want to have a look later at your Macs and see, you know, if you have too many of those, maybe you don't want all of them running. Because in the old way, you were not aware of this thing being added to this dashboard. But in the macOS Ventura way, you would have to manually enable them. So you're more aware of that. So this is something good that Apple did for the user. So let's take everything that we learned today and like try to create some kind of example of an auto update for our client application. This is a classic example where we would want to use background services to do some kind of auto update. If you use MDM, maybe you don't want that. Maybe you would just want to update your app using MDM. But sometimes your app is being sold or distributed to clients that use MDM and some clients that don't use MDM. So you would want to support auto-update as well. So one way you can do that is just prompt the user every time, but this is kind of tedious. And if we can do auto-update that runs in the background and does everything automatically, it's just a way better user experience. So let's see how we can use all of the tools that we saw today to design this kind of auto-update. The simplest way would be to use a LaunchDaemon for an auto-update. Why a LaunchDaemon and not a LaunchAgent? Because installing an app requires administrator privileges. You cannot install an app using user permissions. But the problem is that if we use a LaunchDaemon, then we would need to download the app from the internet. And if you have a software that has administrator permissions that gets to the internet, this is a security risk, and we don't want to do that. So we can do better. Let's do the LaunchAgent do the download the update for us. You don't need administrator permissions just to download and query for an update. We have it as a background service, so even if the internet doesn't work right, even if it crashes, whatever, it doesn't affect our app. It also runs when our app is not running, so even if the user closed the app, you still have this background service that can run and check for updates. And if it does find an update that is available, it can send a message to the LaunchDaemon to install the app that was downloaded. But if the app is running, then you might want to send a message to the user and ask him, hey, do you want to update now? Because we don't want to interfere with the user work. So we have a LaunchAgent checking for update, and he sends a message either to the application that the user is using if it's on, and asks the user, do you want to update? If it does, the application sends it to the LaunchDaemon to install the app. But if the application is not running, it just sends the message directly to the LaunchDaemon. So this is what I said. The client application sends the message to the LaunchDaemon to update. And the LaunchDaemon just receives the downloaded application. And this is the critical part of our design. The LaunchDaemon just gets like a pass to the downloaded application. It needs to verify that the one asked him to update is someone we trust, and we need to verify that the downloaded application is an application that we trust. So we need to double check the bundle ID and team ID and the code signature of the calling process and the process we're about to install. And then we install it. So this is how the LaunchAgent would look like. This is similar to the plist that we saw before. The changes here is that we are using the cron mechanism. So this runs every day at 3 a.m. when probably the user doesn't even use the app. And it also only runs when we have the network available. So this is something we don't need to worry about in our own application. The operating system does it at 3 a.m. If network is disconnected, doesn't matter. Next day it will try to check for update again, no problem. And if everything fails, it will just run again the next day. So we just can leave this code out of sight of our application and make it way more simple. And this is pseudocode of how the LaunchAgent could look like. We check for an update, we download some kind of PKG. We check if the app is running, we're sending an XPC message to the application. If the app is not running, we're sending an XPC message to the LaunchDaemon. And down below is how you initiate the LaunchAgent. It's the same as before. You create an XPC connection, and this is just boilerplate, but the main logic is on top. This is how the client app can look like. Again, if we skip the boilerplate, it just initiates an XPC client. It receives a message. It checks. It asks the user, do you want to update now? If yes, send a message to the LaunchDaemon. If not, then just don't do anything, just skip it. And the LaunchDaemon is the most important part. because this runs privileged, and this is where we want to do most of our security checks. We want to do it everywhere, but specifically here. So again, everything is pseudocode. Don't try to compile it. This is just so it would show on the big screen. So this is the first check. This is, again, we have an XPC connection. We get some kind of XPC message. And before we even do anything with it, we want to make sure that whoever send us this message is someone from a certain bundle ID and team ID. Because for an XPC connection, similar to other WebSockets or Unix domain socket, anyone can send a message. But I can verify that whoever sent the message is someone that is authorized in code, and I can check whether I want to do something with it or just ignore it. So this is the message. And after I get the message and I verify it's from a verified source, I get the bundle ID from the path of the executable from the message. And then I do a static analysis on the executable and check its code signature. It's from a certain bundle ID, team ID, maybe a certain version, any kind of metadata, hash even you can do, whatever you want to make everything secure. And once you do all of those checks, you can install the update with the relevant, with elevated permissions as you need. And it will install the update automatically. No user, without bothering the user. Yeah. The only time you need to bother the user is when you install the first app, because when you install an app, you ask for permission. And when you ask for this permission, it means the user accepts all of this design, all of these background services. And once he accepts that, and we design it in a secure way, we can have our app auto-update. It doesn't mean it's what you want to do. Maybe you always want to ask the user. This is just an example of how you can use those background services to do something in a secure way, with separation of concerns, with separation of permissions, and make your life easier as a client app developer. And that's it. If you have any questions, just raise your hands and we'll head over the microphone.
Yup, any questions? No? All right, well, thank you so much.
If you want to contact me, this is my email address, or you can come by after if you want to ask some private questions. Thank you.